Section: Introduction. In this section, we find ourselves at a crucial point in language modeling. We are witnessing a significant change, as autoregressive language models, which have long been seen as the best option, are now being challenged by diffusion language models for generating language. Recent studies indicate that masked diffusion models, MDMs, are becoming competitive with autoregressive models on smaller language tasks and even surpassing them in generating discrete structures like molecules and graphs. When we scale MDMs to larger sizes, such as those with 8 billion parameters, they perform similarly to models like Llama on difficult datasets in areas like math and science, as well as tasks like completing reverse poems. These findings position MDMs as a strong alternative to autoregressive models. However, we recognize two main limitations of MDMs. First, their inference speed is slower than autoregressive models, mainly because they do not utilize KV caching, which is essential for real-time applications like chat systems. Second, the quality of generation from MDMs shows a significant gap in more complex language tasks. Recently, BD3LMs have been introduced to tackle the speed issue by using a semi-autoregressive generation method, processing fixed-length blocks of text sequentially. This allows BD3LMs to cache previously denoised blocks, making them faster than standard MDMs. Yet, we identify two major drawbacks in BD3LMs. They experience mode collapse when the number of denoising steps is reduced, leading to poor sample quality, and their caching is incomplete, as intra-block diffusion lacks KV support, limiting speed improvements. To overcome these challenges, we propose a new language modeling approach that combines autoregressive and masked diffusion methods. Our model is trained using a hybrid loss that merges the objectives of both AR and MDM, allowing for a smooth transition between the two in terms of perplexity. This requires two key innovations: a new attention mechanism in the denoising transformer that accommodates both AR and MDM generation styles, and a novel training and sampling process that enables KV caching during the diffusion phase, a feature not available in MDMs. Given the unique nature of our hybrid design, we name our method Esoteric Language Models, Eso-LMs. Our approach sets a new benchmark for diffusion models in language modeling tasks and allows for precise control over the balance between AR and MDM perplexities. Unlike previous methods, it supports KV caching during diffusion, resulting in significantly faster inference. In summary, our contributions include proposing a new framework that merges AR and MDM paradigms, outperforming the earlier hybrid approach of BD3LMs, being the first to enable KV caching for MDMs while maintaining parallel generation, achieving up to 65 times faster inference than standard MDMs and 3 to 4 times faster than KV-cached semi-autoregressive models, demonstrating that BD3LMs degrade at low sampling steps, while our method remains competitive in both low and high NFE regimes, and establishing a new state-of-the-art perplexity for discrete diffusion, reducing the gap to autoregressive models. Section Summary. In this section, we highlight a significant shift in language modeling from autoregressive AR models to diffusion language models, MDMs, which are showing competitive performance, particularly in discrete structure tasks. We introduce our novel esoteric language models, Eso-LMs, which combine AR and MDM approaches, enabling faster inference with key innovations like KV caching and improved generation quality, thus setting a new state-of-the-art in language modeling benchmarks. Section: Autoregressive Models. In this section, we discuss autoregressive models and masked diffusion models. For autoregressive models, given a sequence of data, we define the joint distribution by breaking it down into individual components. This means we can express the log probability of the entire sequence as the sum of the log probabilities of each element, conditioned on the previous elements. Typically, we use a causal transformer model for this, which allows us to sample efficiently in multiple steps thanks to key-value caching. These models tend to provide the best likelihood and quality in generation. Next, we look at masked diffusion models, which learn to reverse a process that adds noise to clean data. This process transforms the data into a series of increasingly noisy versions. In these models, the forward masking process operates independently across the sequence, meaning each token is gradually blended with a fixed target distribution. The marginal distribution of the latent variables at a given time is influenced by a decreasing function that starts close to 1 and approaches 0. We also show how the reverse posterior distribution can be expressed for earlier time steps. With a denoising model, we can parameterize the reverse unmasking process over the sequence of latent variables. The negative evidence lower bound for this approach is calculated as a weighted average of losses from masked language modeling, focusing only on the masked tokens. To generate a sequence of a specific length, we start from a defined state and proceed through several steps, sampling each latent variable independently. Once a position is unmasked, it remains unchanged. Since we can denoise multiple tokens simultaneously, the total number of evaluations needed can be less than the sequence length, allowing for quicker generation. However, each evaluation is computationally intensive due to the complexity of the bidirectional transformer used in the denoising model. Section Summary. In this section, we describe autoregressive models that factor the joint distribution of a sequence using a causal transformer, achieving high likelihood and generation quality through efficient sampling. We also explain masked diffusion models, which learn to reverse a corruption process by progressively denoising sequences, allowing for faster generation through parallel token processing, despite the computational cost of the bidirectional transformer. Section: Block Denoising Diffusion Discrete Language Models. In this section, we discuss block denoising diffusion discrete language models, or BD3-LMs, which model groups of tokens in a sequential manner while also using masked diffusion techniques within each group. By adjusting the size of these groups, we can blend autoregressive models with masked diffusion models. We organize tokens into blocks, where each block contains a set number of consecutive tokens, and the total number of blocks is determined by the total number of tokens divided by the size of each block. The likelihood of the entire token sequence can be expressed as the negative log of the probability of the sequence, which breaks down into the sum of the log probabilities of each block. Here, the conditional probability of a block given the previous blocks is modeled using a masked diffusion approach. Next, we introduce esoteric language models, or Eso-LMs, which combine the strengths of autoregressive and masked diffusion models. Our approach has two key elements. First, we create models that can generate tokens both sequentially and in parallel. Second, we modify the transformer architecture to support this hybrid generation. While autoregressive models excel in performance, they generate tokens one at a time, which slows down the process. On the other hand, masked diffusion models can generate multiple tokens simultaneously but often have higher perplexity. We aim to merge these two approaches by generating some tokens in parallel and others sequentially. This leads us to two important questions. How can we calculate the likelihood of this combined model, and how can we adjust the attention mechanism in the transformer to accommodate both generation styles? During training, autoregressive models use causal attention, while masked diffusion models utilize bidirectional attention. We address these differences by designing custom attention mechanisms and introducing sparsity into the attention matrix, which enhances the speed of generation for longer contexts. Finally, we describe how Eso-LMs break down the model distribution into two parts: an autoregressive model and a masked diffusion model. The masked diffusion model generates a partially masked sequence, and the autoregressive model completes the unmasking in a left-to-right manner. Although calculating the overall likelihood directly is complex, we can derive a variational bound using a simple masking distribution. This distribution independently masks each token with a certain probability, leading to a manageable way to compute the likelihood of the hybrid generative process. Section Summary. In this section, we introduce block denoising diffusion discrete language models, BD3-LMs, that autoregressively model token blocks and combine autoregressive, AR, and masked diffusion models, MDMs, for improved language generation. We also propose esoteric language models, Eso-LMs, which leverage both AR and MDM techniques, allowing for hybrid token generation while addressing challenges in likelihood computation and attention mechanisms in transformers. Section: Interpolating between AR and diffusion. In this section, we explore the interpolation between autoregressive AR and diffusion models. When the parameter alpha 0 equals 1, the posterior sample z0 equals x, and all tokens are generated by the MDM, resulting in a 0 AR loss. Consequently, the NELBO loss simplifies to the MDM loss. On the other hand, when alpha 0 equals 0, all tokens are masked, causing the MDM loss to disappear and the NELBO loss to become the AR loss. Therefore, Eso-LMs allow us to switch between AR and MDM approaches, guided by the hyperparameter alpha 0. For sampling, we follow a two-stage process. First, we sample a partially masked sequence Z0 from the MDM distribution, and then we complete it using the AR distribution. In the diffusion phase, we start with a fully masked sequence Z at time 1. Standard ancestral sampling updates only a few masked tokens at each step while processing the entire sequence, which is inefficient. To enhance efficiency, we introduce two main changes. During sampling, we pre-compute the diffusion denoising schedule, where S_T indicates the indices of masked tokens to be denoised at each diffusion step. Instead of processing the whole sequence, we only perform a forward pass over the clean tokens and those scheduled for denoising, significantly cutting down on computation, especially for long sequences. To align with this sampling method, we ensure that the model does not use bidirectional attention over masked tokens during training. This also allows for efficient key-value caching during diffusion. In the sequential phase, we start with the output denoted as ~x, initialized as Z0. The AR model then fills in the masked tokens from left to right, following the sequential denoising schedule. We require the single element sets to be sorted in ascending order. Unlike standard AR decoding, each ~x at position L conditions on both its left context, which consists of clean tokens, and the rightward clean tokens in Z0, allowing for richer generation. We skip evaluations on rightward masked tokens to avoid unnecessary computations. This phase naturally supports key-value caching. We define the unified denoising schedule as S, which combines the MDM and AR sampling schedules. When alpha 0 equals 1, all tokens are generated through diffusion, making S equal to the MDM schedule, while the AR schedule is empty. Conversely, when alpha 0 equals 0, all tokens are generated sequentially, so S equals the AR schedule, and the MDM schedule is empty. For the complete sampling algorithm and an illustrative example, we refer to the supplementary materials. Section Summary. In this section, we describe how our model interpolates between autoregressive AR and masked denoising MDM paradigms using the hyperparameter alpha_0, allowing for flexible token generation. We also outline our efficient two-stage sampling process, which reduces computation by focusing on relevant subsequences during the diffusion phase and supports improved generation in the sequential phase. Section: Designing attention mechanisms for the shared denoising transformer. In this section, we present a unified modeling framework that accommodates both sequential and parallel generation modes using a shared transformer architecture. Our main contribution is a flexible attention mechanism that addresses the differences between autoregressive AR models, which need causal attention and one-step decoding, and multidirectional models, MDMs, which use bidirectional attention. We introduce an attention bias matrix that influences standard attention, where the entries determine whether attention is allowed or blocked between tokens. This setup allows a single transformer to mimic both causal and bidirectional behaviors as required. We propose two variants based on this unified attention approach, Eso-LM-A and Eso-LM-B. Eso-LM-A aims to reduce computation by making attention sparse and applying the denoising transformer selectively to certain masked tokens at each diffusion step. Eso-LM-B builds on this by adding causal masking to both masked and clean tokens, which allows for faster processing through key-value caching, albeit with a slight decrease in perplexity. In the diffusion phase, we identify two inefficiencies in standard MDMs: the need for full sequence forward passes for partial updates and the lack of key-value caching due to bidirectional attention. We tackle the first issue by evaluating only specific tokens at each step. We leverage the idea that masked tokens can be revealed in any order, sampling random sequences during training and applying causal attention to the masked tokens. Eso-LM-A uses this method to cut down on computation while maintaining performance, while Eso-LM-B extends this by applying causal masks to clean tokens, resulting in significant speed improvements during sampling. In the sequential phase, we need to denoise masked tokens produced from left to right. This process is straightforward during generation but complex during training. Each masked token must attend to itself, the clean context to its left, and the clean tokens to its right. Training is challenging because each masked token assumes that the tokens to its left are already denoised. To simulate this, we input a combined sequence of masked and clean tokens into the transformer and create a custom attention mask to ensure proper information flow. The loss is calculated only for the masked tokens. During generation, this issue resolves itself naturally, eliminating the need for concatenation. Section Summary. In this section, we present a unified modeling framework that utilizes a shared transformer architecture to support both sequential and parallel generation modes through a flexible attention mechanism that adapts to the requirements of causal and bidirectional attention. We introduce two variants, Eso-LM-A and Eso-LM-B, which optimize computation and speed during the diffusion and sequential phases by employing strategies like causal masking and KV caching, despite a slight trade-off in perplexity. Section Eso-LM-A. In this section, we introduce Eso-LM-A, which eliminates bidirectional attention over mask tokens in the denoising transformer during the diffusion phase. This change allows us to use a sampling schedule that speeds up inference. Eso-LM-A supports key-value caching only during sequential sampling, but it requires much less computation compared to standard models during diffusion sampling. During the diffusion phase, the denoising transformer takes as input a set of tokens that includes mask tokens to be denoised, and our target is the clean tokens. We randomly order these tokens while ensuring that clean tokens come before mask tokens. We define an attention bias matrix where clean tokens can attend to each other, while mask tokens can attend to clean tokens, themselves, and previous mask tokens based on the ordering we established. We ignore the order among clean tokens and use bidirectional attention among them. Interestingly, if we rearrange the attention matrix according to our ordering, it resembles a prefix language model's attention bias, which we utilize in our implementation. In the sequential phase, the denoising transformer receives a combined sequence of mask tokens and clean tokens. The attention mechanism for the noisy context allows mask tokens to attend to themselves, clean tokens, and the clean versions of previous mask tokens. Clean tokens can attend to all tokens since they are not attended to by others. For the clean context, clean tokens have bidirectional attention, while clean tokens corresponding to mask tokens can attend to both clean tokens and subsequent mask tokens. We again ensure that clean tokens precede mask tokens in our ordering, and we ignore the order among clean tokens, using bidirectional attention among them. When we sort the attention blocks by our ordering, we observe a sparse and structured pattern in the attention matrix, which we leverage in our implementation. Section Summary. In this section, we introduce Eso-LM-A, a modified denoising transformer that eliminates bidirectional attention over mask tokens during the diffusion phase, enabling faster inference with reduced computation compared to standard models. We detail the attention mechanisms for both the diffusion and sequential phases, highlighting how clean and mask tokens interact within a structured attention bias that we leverage in our implementation. Section Sampling. In this section, we discuss the process of sampling during diffusion or sequential sampling. When we have a partially masked sequence, our denoising model needs to clean the masked tokens for a specific subset of tokens. We perform a forward pass on these tokens while ensuring that their positions in the original sequence remain intact. Next, we introduce the attention bias used during this forward pass. We define two sets of indices, one for tokens decoded during the diffusion phase and another for those in the sequential phase. The order in which we denoise the tokens is determined by a specific sequence. At each step, we establish an attention bias that allows clean tokens decoded during diffusion to have mutual attention. A clean token decoded sequentially can attend to other clean tokens from both the diffusion and sequential phases, as well as to itself and any prior sequential tokens. For the mask tokens we need to denoise, they can attend to all previously decoded clean tokens, themselves, and prior mask tokens based on their order. However, mask tokens that are not scheduled for denoising can attend to any token since they are not being attended to by others. This setup allows us to avoid unnecessary computations for tokens that are not currently being processed, which significantly reduces the computational load during the diffusion phase. We illustrate this sampling process with an example sequence, highlighting the use of key-value caching during the sequential phase. We also note that while our first model can utilize key-value caching during sequential sampling, it cannot do so during diffusion sampling due to the bidirectional attention among clean tokens. Therefore, after denoising a set of mask tokens, we must update the key-value pairs for all clean tokens, including the newly denoised ones. To facilitate key-value caching during diffusion sampling, we implement causal attention among clean tokens, leading to our second model, which also shares a key-value cache between the two phases. Section Summary. In this section, we describe our approach to denoising masked tokens during diffusion and sequential sampling, ensuring that positional embeddings are preserved while utilizing attention biases to optimize the process. We also introduce Eso-LMs, which allows for KV caching during diffusion sampling by enforcing causal attention among clean tokens, thereby improving computational efficiency. Section: Diffusion Phase. In this section, we describe the diffusion phase. The denoising transformer takes as input a set of mask tokens, represented as Z_T sampled from a distribution Q_T given X, and our target is X. We utilize the relationship between masked denoising models, MDMs, and attention over attention recurrent models, AO-ARMs. This relationship shows that both mask tokens and clean tokens can be generated in any random order. Therefore, we sample a random order, sigma, ensuring that clean tokens come before mask tokens in this order. In contrast to previous sections, we now restrict a clean token to only focus on itself and the clean tokens that come before it in the order sigma. Similarly, a mask token can attend to clean tokens, itself, and prior mask tokens according to sigma. We define the attention bias matrix A, where the value is 0 if the indices I and j are in the specified order, and negative infinity otherwise. This matrix can be made causal by sorting its rows and columns according to sigma, a property we use in our implementation. Moving to the sequential phase, the denoising transformer receives a concatenated sequence of Z_0 and X as input, where Z_0 contains the mask tokens to denoise. During sampling, we apply causal attention to the clean context from the diffusion phase, which helps us build a key-value cache. To effectively use this cache, we need to maintain similar causal attention among the clean tokens during training. We sample sigma again, ensuring that clean tokens precede mask tokens and that mask tokens are in their natural order. We then replace the bidirectional attention over the clean tokens with causal attention according to sigma. For sampling, we follow the same setup as before, but we replace the bidirectional attention with causal attention based on sigma for the denoising order. The attention matrix A is structured similarly, and we exploit this structure in our implementation. Section Summary. In this section, we describe how the denoising transformer processes input tokens by leveraging a random ordering of clean and mask tokens, ensuring that clean tokens attend only to themselves and prior tokens. We also outline the sequential phase where we apply causal attention to clean tokens while maintaining the structure of the attention bias, facilitating effective sampling and denoising. Section: KV caching in both phases. In this section, we discuss KV caching during both phases of our model. Similar to previous sections, we do not compute future mask tokens. We note that previously decoded tokens, whether generated through diffusion or sequentially, maintain causal attention among themselves. This allows us to use newly generated tokens at a certain step to build the KV cache for the next step, and their cached values can be utilized starting from the following step. For our experiments, we evaluate Eso-LMs on two well-known language modeling benchmarks, the 1 billion words dataset and open web text. For the 1 billion words dataset, we use a specific tokenizer and a context length of 128, reporting perplexity on the test set. For open web text, which does not have a standard split, we reserve the last 100,000 documents for validation, using a different tokenizer and a context length of 1024. All models are based on the transformer architecture, which incorporates rotary embeddings. We apply sequence packing to the 1 billion words dataset, making our setup more challenging and leading to higher perplexities for the same model. We train our models for 1 million steps on the 1 billion words dataset and 250,000 steps on open web text, without conditioning on time steps. The training is conducted on specific GPUs, and we provide detailed hyperparameters and training information in the supplementary materials. Our results indicate that Eso-LMs achieve state-of-the-art perplexities among diffusion models on both datasets, offering a nuanced interpolation between masked diffusion model and autoregressive perplexities. We compare Eso-LMs against leading masked diffusion models and uniform state models, ensuring all models are trained with a consistent batch size. Each batch is split evenly, with half trained using autoregressive loss and half with masked diffusion loss. When training Eso-LMs purely as masked diffusion models, we adjust the diffusion coefficient to reduce training variance and enhance convergence. Our findings show that on the 1 billion words dataset, Eso-LM-A effectively interpolates between the two types of perplexities. Notably, it outperforms the masked diffusion model by about 1 perplexity point when using a specific setting. This improvement is linked to the low variance training loss we discussed earlier. In contrast, Eso-LM-B introduces causal dependencies among clean tokens, which negatively impacts performance compared to Eso-LM-A. On open web text, Eso-LM-B stands out as it is the only model that supports KV caching during the diffusion phase. Trained with various settings, it demonstrates smooth interpolation between the two types of perplexities. As with the 1 billion words dataset, Eso-LM-A remains competitive with the masked diffusion model on open web text. Section Summary. In this section, we describe our approach to KV caching in Eso-LMs, where newly generated tokens at each step contribute to the KV cache for subsequent steps, enhancing performance. Our experiments demonstrate that Eso-LMs achieve state-of-the-art perplexities on standard benchmarks while effectively interpolating between masked diffusion and autoregressive models. Section: Generation Speed. In this section, we discuss the generation speed of our model, Eso-LMs. Our qualitative evaluations indicate that Eso-LMs are 3 to 4 times faster than previous diffusion-based methods that allow key-value caching, and up to 65 times faster than models that do not support this feature. For our experimental setup, we note that diffusion models like MDLM cannot utilize key-value caching because they rely on bidirectional attention. Semi-autoregressive models, such as BD3LMs, can partially cache by generating token blocks autoregressively, but they still do not cache the current block during diffusion. Our method, however, uniquely supports key-value caching throughout the diffusion process. We compared the inference times of Eso-LM-B with MDLM and BD3LMs, using context lengths of 2048 and 8192 tokens, with a batch size of 1. To create a challenging scenario, we set the number of sampling steps to be much greater than the context length, ensuring all methods had a similar number of non-forward evaluations. We found that nucleus sampling added significant overhead, so we disabled it to better analyze the relationship between sampling speed and sequence length. Our results show that Eso-LM-B is approximately 14 times faster than MD-LM for a context length of 2048 tokens and about 65 times faster for 8,192 tokens. When compared to BD3-LMs, which have limited caching, Eso-LM-B is about 3.2 times faster for a block size of 16 and 3.8 times faster for a block size of 4 at a context length of 8,192 tokens. This speed advantage comes from our key-value caching and a scheduler that limits the forward pass to only the tokens that need to be denoised, avoiding unnecessary computations, a feature that BD3-LMs do not have. Although our method is slower than autoregressive models due to delayed key-value reuse, it still outperforms previous diffusion-based models overall. Regarding generation quality, our sampling experiments reveal that Eso-LMs achieve a new state-of-the-art balance between sampling speed and quality. They produce higher quality samples than all previous diffusion models at high non-forward evaluations and do not experience mode collapse at low evaluations, unlike the earlier BD3-LMs. For our experimental setup, we trained Eso-LM-B with different training parameters and generated samples with varying settings to control the number of non-forward evaluations. MD-LM and BD3-LMs used ancestral sampling with specific sampling steps. All generated sequences were 1024 tokens long. We evaluated BD3-LMs with different block sizes, ensuring that certain configurations were not applicable due to resulting values being less than 1. We measured generation quality using perplexity and diversity through average entropy, employing nucleus sampling with a probability threshold. Section Summary. In this section, we demonstrate that Eso-LMs are significantly faster than previous diffusion models, achieving up to 65 times the speed of models without KV caching and 3 to 4 times faster than those with partial caching. Additionally, our method not only sets a new standard for sampling speed and quality but also generates higher quality samples without mode collapse at low NFEs, outperforming prior diffusion approaches. Section: Pareto Frontier of General PPL versus NFEs. In this section, we examine the Pareto frontier of general perplexity versus the number of forward evaluations, NFEs. As illustrated in the figure, at high NFEs, Eso-LM-B outperforms both MD-LM and BD3-LMs, coming close to the quality of autoregressive AR models. However, as NFEs decrease, BD3-LMs experience a significant drop in performance due to their reliance on teacher-forced training. This means that during training, they depend on accurate previous blocks, but any mistakes during evaluation can lead to poor sample quality. Eso-LMs do not face this problem. We also observe that in the low NFE range, increasing the training diffusion parameter improves quality, with a value of 1 yielding the best results compared to lower values like 0.125 and 0.25, while still being competitive with MD-LM. Overall, Eso-LM-B performs well at low NFEs and matches AR models at high NFEs, unlike BD3-LMs. Next, we analyze the Pareto frontier of general perplexity versus sampling speed. We measure the median time taken to generate a single sample across 5 trials for each method and plot this against general perplexity. We find that as the number of trials increases, the median sampling time rises with NFEs, influenced by the method and sampling parameters. For each method, we create a Pareto frontier based on various configurations. Eso-LM-B considers different training and evaluation diffusion parameters and temperature, while BD3-LM and MD-LM focus on their respective parameters. Our findings indicate that Eso-LM-B sets a new benchmark on the speed-quality Pareto frontier. For low sampling time budgets, models trained with a training diffusion parameter of 1 perform best, while those with a value of 0.125 achieve near AR quality under high budgets. Intermediate values, such as 0.25 and 0.5, provide the best balance between speed and quality.